This is the day 21 video. You got homework on page 12 and 13. Make sure to do it on a separate sheet of paper. First one, we converge at x equals 5, and notice our center is -1. So that little diagram I drew there, we know that our interval of convergence is at least that. Centered at -1. On the right, we're going till 5 and including 5 because we're converging at 5. And on the left, we don't know if it's including that other endpoint or not. So going 6 to the left would put us at -7. So we know our interval of convergence is at least that big. Well, if you look at your 4 choices on the bottom, find what's in the center of each of those values. In the first one, you have 0, so that can't possibly be our interval of convergence. Second one, you have 1, so that can't be it. In the third and the fourth, they both have centers at -1, and we said it had to be at least from -7 to 5, including the 5, not including the 7. Well, that matches D, or it could be something bigger, and that's what C is showing. Number 2, we wanted to use our arctan, which they gave us. We wanted to use the third degree, and that should give us pi over 4 if we sub in 1. So you subbed in 1 and minus 1 cubed over 3. That gave us pi over 4. Well, then multiply that by 4 in part A there, and you get 8/3. Well, what is the area of the error of that? Alternating series error bound, go to that next term, the 5th degree term, sub in 1, you get 1/5, but you got to multiply it by 4, remember, so that gives us that our error is less than or equal to 4/5. Now for within two decimal places, that really means we want to be less than or equal to 0.005 due to rounding. So we're putting in 1 for x, remember, that's why we have 1 to the n. We're over the n, and then the times 4 because we had to multiply by 4 to get pi. Well, remember what we're looking for here is the error term. If you go through and solve that, you get n is greater than or equal to 0. And remember, this is trying to tell us the error term. Well, arctan has only odd powers. So that means our error term would have to be the 801st one. Again, because arctan only has odds. With these, a lot of times it's easier to just put in n rather than n plus 1 and know n is the error and then go for the one before, because sometimes we only have odds or evens. So we know 801 is the error term, so the term before that, 799, is our last term that would be included. Well, notice like when we have our fourth term, the degree is 7. So the degree is 1 less than twice our term number. So if we have degree 799, that's 1 less than twice of 400. So we're really, the 400th term is our last term that we would have. Next several, we're just finding our interval of convergence. So do your next term divided by your current term, absolute value, n goes to infinity. When you neaten things up, what I did is I took one of the n plus 1s in the denominator, put that separately, and then had n over n plus 1 all raised to the n. Well, when n goes to infinity, n over n plus 1 is going to approach 1. So that part's just going to be a 1, and then that last fraction, when n goes to infinity, that denominator is going to get huge, so the whole thing will approach 0. That'll always be less than 1, so it converges always, so you have negative infinity to infinity for your interval and a radius of infinity. Next term divided by current term. We have one extra 5 on the bottom, an extra x plus 1 on top. As n goes to infinity, we'll just have that fraction. So multiply the 5s over, subtract the 1s, you get your initial interval. Sub in your -6 and your 4. And for both cases, you could either say it diverges because you got geometric, absolute value of r is less than 1, or you could have said they diverged by the nth term test. So neither endpoint is included in our interval, and our radius would be 5. Next term divided by current term. We have one extra n plus 1 in the denominator, so as n goes to infinity, that will just go to 0. Therefore, our interval is negative infinity to infinity. Radius is infinity. Number 6, next term divided by current term. You'll have a 2n plus 2 in x plus 2's exponent, so there's 2 extra x plus 2's in the numerator. Multiply out your stuff with n's in the denominator and stick them over each other. Notice same degree, so ratio leading coefficients is 1. X plus 2 is squared, has to be less than 1. So therefore, our inside needs to stay between negative 1 and 1. Subtract the 2's over, and you get your initial interval from negative 3 to negative 1, not inclusive. Sub in your endpoints. Negative 1 to the 2n, because it's to the 2n, will always be positive. So we got 1 over n squared plus 2n. We can compare that to 1 over n squared. The n squared over 2n will always be smaller than it. We know the 1 over n squared converges because it's a p-series greater than 1. So by direct comparison test, everything less than that has to converge. So our series we are looking at converges, meaning we'll include the negative 3. And the next one, pretty much same idea because we also got a 1 over n squared plus 2n. I'm not sure why I didn't just write this as 1. You don't need to leave it as 1 over 2n. So pretty much for same reasoning, you got direct comparison test. So we end up including both of those endpoints, and my negative is blending in with my less than sign there on my interval. That's negative 3 to negative 1 inclusive. Next one, next term divided by current term. We get an extra x plus 3 in the numerator. Then I lined up my n plus 1 over n plus 2's, because you can think of that fraction as having the same degree, so it goes to the ratio of leading coefficients, which is 1. And then the radicals, same idea. Think of those both as n to the 1/2. So we just got our x plus 3, subtract the 3's over, you get your initial interval. When you check the endpoints, our terms are getting smaller, signs are alternating, so that converges by alternating series test. When you put in your negative 2, it's not alternating. The gap between our degrees is a half, so let's compare that to 1 over n to the 1/2, which diverges because it's a p-series with p greater than 0 but less than or equal to 1. When we divide those and have n go to infinity, we get a positive finite number. So therefore, our series we're looking at will do the same thing as our nice series. So therefore, the series we are looking at diverges by the limit comparison test. So we're only including the negative 4, and we've got a radius of 1. Number 8, next term divided by current term. We've got an extra 3 in the numerator, an extra x in the numerator. As n goes to infinity, those 2 to the n minus 1 over 2 to the n plus 1 minus 1, basically there'll be an extra factor of 2 in the denominator when n gets huge. So we'll have the 2 in the bottom, so 3/2 to the x, multiply all spots by 2/3. Sub in your x point. I thought of it as 3 to the n in the denominator, so that wipes out the 3 to the n that's out front, so you just have negative 2 to the n. Well, when n goes to infinity, those are roughly going to be the same thing, just alternating signs, so that's going to diverge by nth term test. And pretty much same idea for the positive 2/3, just it's not alternating. It's still not approaching 0, so diverging by the nth term test. So we did not include either endpoint, and our radius was 2/3. So part A, find the interval of convergence, kind of like we've been doing for the others. You get 2 to 4 initially. When you sub in the 2, it would converge by alternating series test because the signs are alternating and it's getting smaller each time. For the other one, though, we've got this 2 on the bottom, so essentially you can pull the 1/2 out. 1 to the n will just be 1. and then that's the harmonic, so it diverges. So we included the 2 but not the 4, and our radius was 1. Now I put the radius there, I think just as a habit from 3 through 8, but it didn't ask for the radius, you didn't have to have that. So now we want f prime as a power series. So do your derivative. The n multiplies out front and wipes out the n that was in the denominator, so we're now raised to the n minus 1. Remember, our derivative will differ at most for an interval of convergence by the endpoints. So recheck your 2 and your 4. Well, we got negative 1 over n minus 1 to the 2, so as n becomes huge, the numerator is just alternating signs, so that's never going to approach 0, so that diverges by the nth term test. Same thing for the other one, so we don't include our endpoints. And when we do our integral part, so we'll do our antiderivative and sub in x and 3 essentially. So this will be capital F of x minus capital F of 3. Well, subbing in a 3 makes all zeros, so that part's going to all be gone. Because we're subtracting them, any c's would wipe out, so you don't have to worry about that. So we just had to do our antiderivative. So the n went up to n plus 1, divide by n plus 1, which is now in the denominator. So subbing our endpoints, we get now, because there's n's in the denominator, and it does alternate, it will converge by alternating series test. When you put in the positive 4, we've got to do a comparison of 1 over n squared, which we know converges by p series with p greater than 1. Well, when there's all that extra stuff in the denominator, that'll always be smaller than our nice one. So that's just going to converge by the direct comparison test, meaning we include both the 2 and the 4. Find the interval of convergence. Should initially get negative 1 to 1. When you check the endpoints, the negative 1 get an alternating series because they're getting smaller. With the second one, you can compare it to the harmonic, which we know diverges. Divide them, and n goes to infinity, you get a half. This should say a half is greater than 0 here, because we want that to be a positive finite number. So therefore, our series does what the nice one does, because the harmonic diverged. Our nice one diverged by the limit comparison test. So we're only including the negative 1 in our interval. And again, it didn't say that we had to say the radius. So now we want to find f of negative 1 with our 4th degree polynomial. So sub in 0, 1, 2, 3, and 4 for n. We get that, put in the negative 1, and we get 263 over 315. Alternating series error bound, we get 1/11th for our maximum error. So take our answer from B, and that could have either been added or subtracted. So subtract the 1/11th, add the 1/11th, and we know f of negative 1, the actual value, falls somewhere within there. You will often see it written like that, where they don't even add or subtract the fractions together for that. All right, in our notes packets, we'll be on day 21. We're going to look at Taylor series today. So Taylor series is a power series that represents a specific function. Taylor series means it could be centered anywhere. If it's a Maclaurin series, that means it's centered at 0. So that terminology kind of similar to our Taylor polynomials and Maclaurin polynomials. So now what's the difference between it being a polynomial or a series? So let's say we've got e to the x. Written there is what we've seen for e to the x when it's centered at 0. Notice it ends. So therefore, the Taylor polynomial is an approximation for e to the x. We saw that you could make it a better approximation by just adding more terms. Now, a Taylor series, notice it goes on infinitely. The Taylor series is not an approximation, it is the exact function. Because it's going on infinitely, it represents the exact function. It is not an approximation. So that is the difference between the Taylor polynomial versus the Taylor series. So to build your Taylor series, it's very similar. You've got your function value at whatever derivative over x minus your center raised to that power of whatever the derivative is over that factorial. Remember, if your center is at 0, we consider it a Maclaurin series. And things are very similar to the polynomials we already saw, just now we're going on infinitely, and that then represents the exact function. So why are Taylor series helpful? Well, sometimes things we can't find the antiderivative or the derivative based on what we have, so the Taylor series can allow us to do that. So here's an example. Let's say we want to do our integral of e to the negative x squared dx. We do not have techniques to just do that directly. But with Taylor series, we can find a representation of that. So we have e to the x. E to the x was all additions. It had every power and every factorial. So in our series notation, starting with n equals 0 and going to infinity, we'd have x to the n over n factorial. E to the negative x squared means sub negative x squared in for all the x's. So we would have 1 minus x squared. Negative x squared squared would be plus x to the 4th over 2 factorial. Then we would have minus x to the 6th over 3 factorial plus dot dot dot. Our general notation, if you take a negative x and sub it in for x in our general notation, we'll have a negative 1 to the n, and then we'll also have an x to the 2n. So we kind of split up that negative x that we're subbing in and think of it as negative x to the n and then x squared to the n, and then that's all still over n factorial. So if we do our integral and do our antiderivative, it's an indefinite integral, so we're going to have a c. We usually put that c out front so it doesn't get lost in the dot dot dot. So we're going to have c plus x minus 1/3 x cubed plus we're going to have x to the 5th, and we're going to have over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial plus dot dot dot. So that's going to equal, we usually put our c in front of the summation, plus our summation, n equals 0 to infinity. So we'll have negative 1. Exponent had to go up 1, so we have 2n plus 1. Divide out front by that 2n plus 1, and we still have our n factorial. And then just check a couple of them to make sure they work. When you put in, oops, I forgot my raised to the n on the negative 1. When you put in 0 for n, we get a positive back. We'll have x to the 1st, that matches up, and then we'll have 1 times 0 factorial, so x's denominator was just 1. When you put in 1, we'll have a negative. We'll get x to the 3rd on top, and we'll have 3 times 1 factorial, so we get that 3 in the denominator, the 1/3. So it looks like that is all checking out. So can we find our value of c? Sometimes we'll be able to, sometimes we will not be able to. And it all depends on if what we're trying to represent, we know a point for that. Well, integral of e to the negative x squared, we did not know any values of. So in this case, we cannot find our c. So this would be all that we would have. If we could find that c, or if we knew a point, we would sub in and then determine what that value of c was. Well, we're going to, down on the bottom, now use that to evaluate a definite integral. Well, if we were going to do this definite integral, we would have whatever our antiderivative is with 1 subbed in minus our antiderivative with 0 subbed in. Remember that would, the c's would wipe out, so we don't have to worry about the c's here. Well, notice that when x is equal to 0, every single term is going to be 0, so that would be gone. So really, we just have to worry about capital F of 1. Based on the fact that we've got a -1, we've got an alternating series here. So we want to be thinking alternating series error bound if we want to be within 0.001. Remember, we're doing capital F of 1, so where that arrow is pointing, that x is going to become a 1. So basically, that whole top we're not going to worry about because alternating series error bound, we do the absolute value, so we don't care about the -1 when we're finding our error term. The x is becoming 1, and 1 to the 2n plus 1 is just 1. So, in reality, we just care about 1 is 1 over n factorial times 2n plus 1, and I just reversed how they were in the denominator, going to be less than or equal to 0.001. So what we're going to do is we're going to graph this, and keep in mind, the first n where that is true, that is the error term. It's helpful to do it this way when we have things that have both odd and, or either just odd or just even powers. Here we have just odd powers, so it's helpful to know that. Okay, so let's go to a calculator and go to the graphs page. And we're going to have 1 over, remember we've got to put it in as x. So we've got x factorial. Sometimes it likes the times next to the parentheses, so you might want to put that in. And we'll have 2x plus 1. Do a control T. And we're looking for the first one that is less than 0.001. Remember, it'll usually switch to scientific notation, so be careful. So there's 0.004, that's too big. And notice this one now has switched to scientific notation. If you move that 4 to the left, that's really 0.0007, which is less than 0.001. So that means n equals 5 is the error term. So let's see, we have 0.0007575. And at 4, we had 0.0046. So that's the work I would want to see so that it's clear that, all right, n equals 5 is the error term. So that means we want to go out to n equals 4. So n equals 4, if we go back here, this one was n equals 0. That one was 1, 2, 3. So whatever that next term is, that'll be the fourth term. So we got to go out to the 9th degree term. And we're going to be subbing in 1 for all of the x's. So if we go down here, we're going to have 1 minus 1/3 times 1 cubed plus, then we're going to have 1 to the 5th over, we'll have 2 factorial times 5 minus 1 to the 7th over 3 factorial times 7 plus 1 to the 9th over 4 factorial times 9. So if we sub that all in, we should get 5651 over 7560, or whatever that is, rounded to 3 decimal places. Moving on to the next page, we're going to come up with a Taylor series for 1 over x. 1 over x is undefined at x equals 0, so we have to pick a different center. We can't do a Maclaurin series. So we're just going to pick something convenient, so we'll use c equals 1. So first, let's find several of our derivatives at x equals 1. So that's really x to the -1, so that would be -1 x to the -2, or in other words, -1 over x squared. If you have -1 x to the -2, do its derivative and you'll get 2 x to the negative 3. So that's 2 over x cubed. Do its derivative, you'll get negative 6x to the negative 4th, or negative 6 over x to the 4th. And do one more, we'll get 24x to the negative 5, so that's 24 over x to the 5th. We'll evaluate those each at 1. So we're going to get 1, negative 1, 2, negative 6, and 24. So we want to represent 1 over x. So to start out, it's our value of 1 over x at 1, x minus 1 to the 0 power, which is gone, and then that's over 0 factorial. Next we have minus 1. We'll have x minus 1 to the first power over 1 factorial, plus 2 times x minus 1 to the second power over 2 factorial. So we're just building this out. Minus 6 times x minus 1 to the 3 over 3 factorial, plus 24 times x minus 1 to the 4th over 4 factorial, plus dot, dot, dot. Well, something I want you to notice is 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. So this is really going to be 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed plus x minus 1 to the 4th, and so on. So the series, we could write it as n equals 0 to infinity. We've got an alternating sign there, so let's do negative 1 to the n, because we need it to start as positive, and then we'll just have x minus 1 to the n. So we don't have to worry about those factorials because they ended up dividing out. So we're going to use our answer from above to do a Taylor series for natural log of x. So remember, from up above, 1 over x we just said was 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed plus dot, dot, dot. And we said that it was the summation n equals 0 to infinity of negative 1 to the n times x minus 1 to the n. So we want to think antiderivative. Notice this is an indefinite integral. So we're going to need a c. So we'll do c plus antiderivative of 1 is just x. X minus 1's antiderivative. Technically, you're going to need a u substitution, but the du is not going to have any correction. So we don't really need to worry about it. So we'll have minus x minus 1 squared over 2. Plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4 plus dot, dot, dot. So we'll write that as a general series momentarily, but let's think about the c first. Is it possible to find the value of c? Well, we do know some values of natural log. A nice one is that we should have the point 1 comma 0. So when we put in 1 for all the x's, we should get 0 back. Well, that means 0 should equal c plus 1, because all those other terms, the 1's going to wipe it out. So in other words, c is going to equal negative 1. So this is really going to be negative 1 plus x, which I'm just going to write as x minus 1. And then minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4 plus dot, dot, dot. So this one we were able to find the actual value for the c. And now let's see if we can write this as a summation. So we're starting with positive again. So if we start with n equals 0 to infinity, we'll do the -1 to the n again because we're starting positive. Notice our first exponent is 1 though, so we're going to have x minus 1 to the n plus 1 all over n plus 1. And that kind of makes sense with our antiderivative. Notice from the 1 over x, our series, the exponent went up 1 and we divided out front by n plus 1. If we had had a c that we didn't resolve, we just would have put c plus right there. So if we had a c, it would go there. But we didn't. We were able to resolve that, and it just worked into our summation. So we're going to use this now in the last part for this video. We're going to find our interval of convergence for natural log of x. So going back, remember we just found this was our series. So maybe I'll just rewrite that over here just to remind us. N equals 0 to infinity. We had -1 to the n. We had x minus 1 to the n plus 1 over n plus 1. So for interval of convergence, we'll do limit as n approaches infinity. We'll do absolute value of our next term divided by our current term. Don't need to worry about the -1 because we're doing absolute value. So we're going to have x minus 1 to the n plus 2 over n plus 2, that's our next term, times reciprocal of our current one, so we'll have n plus 1 over x minus 1 to the n plus 1. So we'll have one extra x minus 1 in the numerator, times, we're going to have n plus 1 over n plus 2. This is just going to go to 1, so we're just going to have absolute value of x minus 1, which needs to stay less than 1, so it will converge. Write that without the absolute value, we'll have -1 less than x minus 1 less than 1. And when you add the 1's over, we'll have 0 less than x less than 2. So that's our initial interval of convergence. We now have to check the endpoints. So we'll start with x equals 0. So when we sub 0 in to our original series, we're going to have the sum of n equals 0 to infinity. We'll have -1 to the n. We'll have -1 to the n plus 1 all over n plus 1. So this can be rewritten. Our numerator is going to be a negative regardless of what n is, because we're going to get either a negative times a positive or a positive times a negative, so it'll always end up as a negative. So we have -1 over n plus 1, n equals 0 to infinity. Well, we could pull that -1 out front. And when you put 0 in, the denominator is 1. When you put 1 in, denominator is 2. Well, we could just redefine this, put an n equals 1 on the bottom, and have this as 1 over n. That's the same series. Subbing in 0 to the one on the left would give us a 1 on the bottom, then 1 would give us 2, and so on. But subbing in 1 now will give us 1, and then 2, and so on. So it's the same thing, and the reason for doing this is something we know. We know this diverges since harmonic. So if you could rewrite the series in a different way that meets our needs for a quick determination, if it is converging or diverging, that is fine. So now we'll check x equals 2. If we put 2 into our original series, that -1 to the n plus 1 is now 1 to the n plus 1. Well, imagine this 1 to the n plus 1. I should say 1 raised to anything is just going to be 1. So this is like -1 to the n over n plus 1. Well, as n gets huge, our terms are going to get smaller. So an plus 1 is always going to be less than an. And our limit as n approaches infinity of our terms will go to 0. We have alternating signs, so we can say this converges by the alternating series test. So we are going to include the 2 but not include the 0. So therefore our interval is 0 less than x less than or equal to 2. So that means as the terms get added, the graph of our series will match the graph of natural log of x on that interval. That's it for this video. Have a great rest of your day.